Okay, welcome to Chapter 9. Chapter 9 is an interesting one as we are going to study alkynes. Now, we want to remember the alkyne functional group is a triple bond, right? Two carbons connected by a triple bond. We're going to see a lot of chemistry reminiscent of Chapter 8 with the alkenes with some variations. But we're going to see the same kind of pattern where we talk about the functional group and then do the nomenclature, how to prepare them, and what can we do with them. So let's jump into a little bit of discussion on what is an alkyne, right? What is special about this functional group? So you know that a triple bond has a sigma bond. That's that bond that you see there in the middle, right here, right? That head-to-head overlap. You have two pi bonds. You've got a pi bond between these two p orbitals above and below, and then the two p orbitals that are coming out in the front and those sneaking back there in the back. All right, so you have one sigma, two pi. It's linear. There's no rotation around the bond. You have a lot of electron density right there in the center, right? We've got 6 electrons located in this bond. Many addition reactions of alkenes also work on alkynes. There will be another spider diagram up for you on eCampus. Same kind of practice as you see with your alkene spider diagram. In nature, just like with any of the functional groups we're learning about this year, they're in general sophomore organic because they're found in lots of places. They're important functional groups. A common name that you'll see is acetylene. That's one that I'm going to ask you to know. It is just 2 carbons with a triple bond. It's the simplest one. It's used in blowtorches, and it's an important precursor for synthesis. We're going to talk about multi-step synthesis again at the end of this chapter, and this is going to be an important starting material. There's 1,000 different alkynes in nature. This just happens to be one example. And here is another example of a synthetic alkyne, ethinyl estradiol. It's an active ingredient in birth control. All right, just Klein likes to pick out some random examples to show you. Naming. You are going to see this general slide over and over again when we come up on nomenclature. You're going to notice, though, there's the same basic steps. Right? You're going to identify the parent. You are going to identify the substituents. You are going to assign locants, and then you are going to order alphabetically. The main difference here now is the parent is you're going to take that parent and drop ANE, and you're going to add YNE. And this is going to be the longest continuous chain with the triple bond. One too many. With the triple bond. So while we might name something like this pentane, right? If we have a triple bond, this is going to be 1-pentyne. Yes, pentane, pentene, pentyne. You do have to number these. Now, notice how Klein drew this here. This is more correct, right? You've got a 180-degree bond angle when you're dealing with a triple bond. Sometimes people have a hard time counting, right? This is 5 carbons and they might leave one out. So you will often see me put it at an angle. It's not correct geometry. But I think it's easier to count. You've got 1, 2, 3, 4, 5 carbons. It does not matter which one you do for me. But what is important is that you don't lose or gain carbons here. The alkyne is a higher priority functional group than alkane, as are most things other than halogens. And so you want to find the longest continuous chain that has that high priority functional group. So while in this example, that longest chain, that octane, would be the parent, in this example where we have the triple bond, the parent needs to contain the triple bond. So you have 1, 2, 3, 4, 5, 6, 7. That parent is going to be heptyne. You want to give the numbering, just like with alkenes, you want to give the lowest locant possible to that functional group that gives you the parent name. So even though there would be, in this example here, there would be a 2, 3, 3 versus a 5, 5, 6, we're going based on the alkyne, right? So this one, if we were going to name it, would be, and so, right, over here, that's how I've connected that. Ooh. Oh no, where did my, there we go. Okay. Let me just draw this really quickly. 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. All right, I made some choices here where I seem to have flipped it over, right? That's how I might draw it, where I've got the bend. This is going to be a 5, 5, 6 trimethyl. 2, you do have to say where that triple bond is, 2 heptyne or hept2-ine. That would also be acceptable. The two ways that we could do this. This part is just a personal preference. I understand both. You will see me use this most frequently until we start to have multiple things that affect the parent, and then I will go to this one. We'll talk about that in just a moment. All right, now there's only one common name that I want you to know, and that is ethyne, right? This is the IUPAC name, but the common name is acetylene. You need to know that. Right, so acetylene is the common name for ethyne. These are also common names, but they're all based on acetylene. So as long as you know acetylene, you might be able to deduce what these are. Terminology that's also important, terminal versus internal. If you have a triple bond at the end of the chain, it is considered terminal. If it is inside, if there's an R group on both sides, it's internal. Terminal alkynes have a hydrogen on the end, and that winds up being very important for reactivity. Terminal alkynes and internal alkynes have different reactivity. That knowing the difference here is important in spectroscopy, like when you look at IR. So you will hear terminal and internal quite a bit. Now, as far as naming, I do want to talk about one more thing. Right, so nomenclature, continued, right? If you have the ene and the ine. The ene is the higher priority, but they both affect the parent. They're both weird that way. They affect the parent even if they are not the highest priority that gives you the suffix at the end. So if you have both of them, it's going to be an enine, right? That is going to be the ending. But you have to number both of them, and I'll show you, this is where I do tend to put the numbers inside the parent. Let's say we have something like this. Because the ene is the higher priority, we would number to give the ene, 4, 5, the lower numbering possible. This would be based on pentane, but it would be a pent-ene-ine. And this is where I would put the numbers for the double bond inside here. I have a 2-ene, 4-ine. Now, it's just en, not ene. It's not a big deal if you mess that up. What is important is that you number it so that it's clearly the double bond is at 2, the triple bond is at 4, pent-2-ene-ine. I highly recommend, as with all nomenclature, practice. All right, make sure you do some practice on this. You will see this pop up on your next exam. All right, now continuing on talking about our properties, especially when we think about the terminal alkyne, we have some interesting properties with acidity. Right, when you have a proton attached to a triple bond. We talked about this in chapter 3. It's not a strong acid by any means, but it is a lot more acidic than an H on an sp3 or an sp2 carbon. So there is this special acidity here, means it's easier to remove that proton. Now, it's not acidic, right, like a normal acid that we think of, but we can remove it if we have the right kind of base. Most acid-base steps are equilibrium steps. So, let's see, if we have the right base, we can remove that proton and get the acetylide ion. But we have to be thoughtful about which base we pick, right? So if we pick something like, let's move on to this slide. If we pick something like hydroxide, well, the pKa of water is lower than the pKa of the terminal alkyne, so you're not going to get a lot of product there. Hydroxide bases are not good enough bases to remove this proton right here. What you need is an amide base. This is a much stronger base. NH3 is a base, and that is the conjugate acid of NH2 minus. The amide ion is going to be a much, much stronger base for us. So when we are trying to remove a proton, and you may see equilibrium arrows here, you may not, you're going to see NaNH2. So just like you saw with NaOH or NaOCH3 or NaBr, all this is your counter ion, right? The sodium is there, but it is not part of the reaction. It's going to be the NH2 minus that is going to be deprotonating, right? In a very simple, concerted step, leaving behind that anion, that carb anion, right? And then the Na plus is just there as a counter ion. You can write it. You don't have to. Usually I'm just asking for the organic product. If you're on sapling and it's asking for everything in the inorganics, then you'd have to include that as well. Now, what do we see here? This is going to come up again in reactions of alkynes. This is a strong nucleophile. So we are going to see some substitution reactions later. All right, so keep that in mind. That will be in another lecture portion. All right, it's also called the alkynide ion. That's just, if you have whatever R group there, you will hear me say acetylide ion quite a bit. Just know when I say that, I'm talking about the negatively charged triple bond. Okay, and that's just comparing acidity there. Now, preparing alkynes, and that's where we'll leave off in this video. Preparation, how can we make them? Right, all of these things are really important once we get into multi-step synthesis. So we know how to make an alkene, right, from an elimination reaction. We need a good leaving group and a proton nearby, and you're going to use a strong base, whether it's sodium hydroxide or methoxide or a bulky base like your tert butoxide. That will remove HBr and leave you with a double bond. Very similar, to make a triple bond, you need to remove 2 leaving groups, 2 protons. You need a dihalide. So there's a couple of different options here, and I'm just going to do kind of a generic, just a random starting material. You could have a geminal dihalide, and you could treat it with the base. Now, in this case, the base that you want to use is going to be NaNH2. You are going to want a strong base here. Okay, yes. So that will lead you to your triple bond. Now, this will also work if you have a vicinal dihalide. All right, so vicinal means they are on adjacent carbons. We're still going to be losing HBr twice. We're still going to use NaNH2, but now we just have the H and the Br are set up just a little bit different. So all you need is an alkyl dihalide, and it can be geminal or it can be vicinal, either on the same carbon or on adjacent carbons. Both will work. These are both eliminations. Now, it does go by an E2 mechanism. The vicinal dihalide's a little bit different. You will not be asked for this mechanism. You may need it for multi-step synthesis or product prediction, but you will not be asked for this mechanism. We've already done E2. So, okay, what's important to note here? You do need two equivalents of NaNH2. Oftentimes you will see that left out because if you don't have enough NaNH2, it's not that it's going to necessarily stop at the alkene, though it might. You may just get a weird mixture of products. If it makes you, feel more complete, you might put a 2 out here just so we know 2 stoichiometric equivalents. It's all right by me if you just put NaNH2. Something else you might see, NH3, this is our solvent, right? We're just doing this in ammonia. You don't have to put that there, but I want you to be aware of what it is if you see it. Let's see. If you've got a terminal alkyne, right, it may also deprotonate here. That would not happen in the examples I drew because I drew internal alkyne formation. This is just another example here. You have a dihalide. You have excess NaNH2. That was the point. Okay. Why do you have this second step of water? Well, if you make a terminal alkyne, this proton is going to be very acidic. You're in a very basic environment. And so 2 is just to provide that hydrogen, put it back on there, bring that pH back down, right? So that would be the reason why you would see a second step of water there. It's typically only seen